Welcome to Physics Uncomplicated. Sit back, relax, and enjoy as you learn the key concepts of physics. Each chapter in this series is intentionally kept to a maximum of 12 minutes to convey only the essential facts and ideas for that particular topic. You may use these videos as a supplementary aid to refresh your understanding of the chapter. Wishing you all the best.
Before we start our chapter, let's take a moment to introduce the characters who will appear throughout this animated series in both the Class 11 and 12 videos.
Good morning, students. I hope you're all wide awake because today we begin one of the most exciting and foundational chapters in all of physics, laws of motion. In the 4th century BCE, Aristotle explains to his students that a cart requires a continuous force to keep moving. He uses the example of a man pushing a cart. When the man stops pushing, the cart comes to a halt.
But Professor, the other day I was in the lab pushing the trolley. I left it as soon as I heard the class bell, but noticed the trolley continued to move for a distance before stopping. Oh, it's time for class.
Absolutely, Meera. Aristotle's conclusions were not entirely accurate. We refer to this as Aristotle's fallacy. Aristotle had concluded that motion cannot continue without a continuous force. To him, rest was the natural state of objects. This idea made sense at the time, but he overlooked something invisible but powerful: friction. Over 1,000 years later, in Renaissance Italy, a young mathematician named Galileo Galilei began to question this belief. To find the truth, Galileo conducted an experiment. He rolled balls down smooth, double-inclined planes. Then he observed how far they would roll up a second incline. Each time the ball climbed nearly to the same height it started from, even if the second slope was less steep. He asked, what if I made the second slope flat? Would the ball roll forever? Of course, in reality it didn't. Friction still slowed it down. But Galileo reasoned that without friction, the ball would never stop. That's when he had his revolutionary insight. An object in motion stays in motion unless acted upon by an external force. This idea became the foundation for Newton's first law of motion, also called the law of inertia. Imagine pushing a sphere in space. The sphere continues to float endlessly. This illustrates Newton's first law. A body remains in its state of rest or uniform motion unless acted upon by an external force. When an airplane is flying on Earth, it moves through the atmosphere, which is filled with air molecules. These air molecules exert an air resistance on the aircraft, opposing its motion. This means that real-world environments like Earth always involve external forces such as gravity, friction, and air resistance, making perpetual motion impossible. Let's illustrate Newton's second law with an example. Imagine you are pushing two balls, one with a mass of 10 kilograms and the other with a mass of 5 kilograms. When you apply the same force to both balls, you notice that the 5-kilogram ball moves further than the 10-kilogram ball. This demonstrates that the acceleration of an object is inversely proportional to its mass. Consequently, a higher force is needed to push objects with greater mass compared to those with lower mass. Mathematically, Newton established that the pushing force F is equal to the mass of the body multiplied by the acceleration it achieves. Newton's third law states that for every action, there is an equal and opposite reaction. For example, when a boy swims, he pushes the water behind him, which propels him forward. In another example, a rocket burns fuel and the exhaust gases are expelled from the back of the rocket, pushing it upward in the opposite direction. The law of conservation of momentum states that the total linear momentum of a system remains constant if no external forces are acting on it. In a collision, the combined momentum of all objects before the impact is equal to their total momentum after the impact. In billiards, when the cue ball collides with another stationary ball, the law of conservation of linear momentum applies, provided the collision is isolated and external forces, such as friction or spin, are not significantly considered. Momentum is represented by the symbol P and is calculated using the formula P equals mass into velocity. In the context of billiards, we can derive the formula for the conservation of momentum as follows. Let's assume that the cue ball, ball 1, has a mass m and an initial velocity of u1. The target ball, ball 2, also has the same mass m and is initially at rest, so we can say u2 equals 0. After the collision, ball 1 moves with a velocity v1, ball 2 moves with a velocity vv2. According to the law of conservation of momentum, the total momentum before the collision should equal the total momentum after the collision. This can be expressed as mu1 plus mu2 equals mv1 plus mv2. Since u2 equals 0, the equation simplifies to mu1 equals mv1 plus mv2. This shows that the momentum of the system is conserved during the collision. Imagine a scenario where a woman is suspended from a rope while mountain climbing. She remains safely in place because the tension in the rope pulls upward, balancing the gravitational force pulling her downward. As a result, the net force acting on her is 0, allowing her to stay suspended without falling. This example illustrates the concept of equilibrium of a particle. Imagine a car taking a turn on this curved, inclined road. This is what we call a banked road. Now, when a vehicle negotiates a curve, especially at high speed, a special arrangement is needed to provide the necessary centripetal force. That's where banking comes in. Let's break it down. The surface of the road is inclined at an angle theta to the horizontal. 3 primary forces act on the car. First, its weight mg, acting vertically downward. Second, the normal reaction n, perpendicular to the surface of the road. And third, if friction is present, the frictional force F, which can act either up or down the slope, depending on whether the car is slipping inward or outward. Now, here's the beauty of banking. Even without any friction, a properly banked road can allow the car to make the turn safely. That's because the horizontal component of the normal force provides the necessary centripetal force, which is given by mv squared by r, where v is the speed and r is the radius of the curve. When we resolve forces, the vertical components of the normal force and weight must balance each other out to ensure the car doesn't rise or sink. That gives us r cos theta equals mg. For the horizontal direction, we get r sin theta provides the centripetal force. So combining both, we get tan theta equals v squared by rg. That's the ideal condition, the angle at which no friction is required. If the car moves faster or slower than this ideal speed, friction comes into play to either assist or oppose the motion.